All right, so what are energy conversions? Converting of one form of energy into another. Everything you see is a result of an energy conversion of some sort. Okay, let's begin by Hank explaining it to you.
Now, none of those forms of energy are the forms of energy that the ancient generals were interested in, of course, but I wanted to illustrate how much energy really is in there. What the ancient generals were interested in was the system's gravitational potential energy, because this heavy thing here, which is full of pennies, oh god, that's dangerous. This thing is heavy, it's full of pennies, and it has been lifted up, and the force of gravity is trying to pull it back down. This stored gravitational energy is a form of potential energy, that is, energy contained within a system because of its position. This does not mean that it has the potential to become energy. It is energy. It's just stored. If it wasn't there, and then it was, then you would be creating energy. And as we all know, you cannot create energy. Like, we all do know that, right? It's the first law of thermodynamics, also known as the law of conservation of energy, which is a real hard and fast, not just unbreakable, but unbendable law of physics. Energy cannot be created, and it cannot be destroyed. The amount of energy in the universe is constant. And since everything is energy, the amount of everything in the universe is constant, which is a little bit trippy.
So, what are some different types of energy? Copy them down. Chemical, electrical, electromagnetic, light, sound, mechanical, electrostatic, and magnetic. Mechanical may be the only thing that you're not familiar with. Mechanical is just simply what we call the energy of moving things. So this Matthew here moving in and out of the room is demonstrating mechanical energy. Mechanical energy. Okay, the other forms of energy you should be familiar with. So really anything that we see happening today can be described by some kind of energy conversion. For example, for me, you're hearing me talk, you're watching me, okay? That is energy conversions. I am converting my chemical energy found in glucose in my cells, and that's the glucose are burning, making my muscles work. That's mechanical energy. And I'm pushing air through. That's more mechanical energy. And as the air pushes through my larynx, it is being converted into sound energy. Those molecules move through space. They vibrate your eardrums. The sound energy is then converted back into mechanical energy, and eventually that is converted into electrical energy, which goes up into your brain, and it does all sorts of funky things that allow you to hear and understand. Well, you're hearing, but you're hearing, period. But you're not understanding until that sound is converted into electrical energy. Okay? So, drying your hair. Look at the energy that we have up there. Explain to me what energy conversions are involved in drying your hair. Jackson, start with, very good, starts with electrical energy. Then it's converted, that electrical energy is converted into somebody new. Yes, Bailey. Heat, very good, because it needs to have, the air coming out of the dryer needs to be hot. Okay, so what other conversions? Somebody besides Jackson and Bailey, come on. Sound, do you hear a sound coming from the hairdryer? By the way, does the sound help you at all? No, so that is wasted energy. It would be better if the dryer had absolutely no sound. That would make it more efficient. So if you're hearing a sound, then some of the electrical energy you're putting in there is just wasted. That's just money. That's why the more expensive the dryer you have, usually the quieter it is. Okay. Next, what is another energy conversion taking place? Light. Do you sometimes see some light coming from the coils? Yeah. Okay. So do you need the light to dry your hair? No. That's wasted. There's another form of energy which is important, and you do need it. Mechanical. In what way? Yeah, you got to make the fan move in order to move air. In order to move air. Photosynthesis. What about photosynthesis? What? Electromagnetic, which is light, being converted to chemical. Very efficient. Some of it is being converted into heat, but by and large, Mother Nature is far more efficient than we are when we make machines. Mechanical machines are not as efficient as biological machines. Last one. This one's hard. Gasoline to rear window defrosting. Starts with what?
Electrical?
No. Chemical. Gasoline is chemical. Okay, so the gasoline is burnt to do what? What does it produce? Heat. And what does the heat do? No. The heat for defrosting the window does not come from the heat that's liberated in gasoline. The heat that is liberated in gasoline does what to your car, gang? Makes it move, which is what kind of energy? Mechanical. So all the internal engine parts move because the pistons, right, move because of the heat that is generated by the chemical energy. Okay? The mechanical energy. So you have the engine moving parts, and what does that produce? Okay, that's wasted. That really doesn't go into defrosting the window, though you are right. What energy form is it converted into in order to? Electrical. There's this box, it's a magic box called an alternator. And the alternator takes mechanical energy and converts it into electrical energy, which powers your car. Your battery does not power your car. Your battery starts it, and when it's turned off, your battery may power your radio or your power windows, but your battery does not make your car go. Okay? Your alternator makes your car go. And your alternator will then go and replace the battery power that you lost in getting your car started. So it'll recharge your battery.
Doesn't the battery make it go into Prius?
Well, yes. I'm talking about an internal combustion engine here. Okay, finally, electrical to what? To defrost your rear windows. Heat. Yeah, we cannot get the heat from burning. I mean, if we were to convert chemical to heat in order to defrost the rear window, then what we would do is probably get a blowtorch and wave the blowtorch over the window and probably crack the window. But that would be chemical to heat in order to defrost the window. Yeah, no. Okay, what are the two problems associated with any kind of energy conversion? And this is, we've already talked about it. Along the way, you will lose energy. In your dryer, you lose some of the energy in the form of light and sound. Your car loses most of the energy. What do you think? How efficient is a car in percentage? In other words, how much of that gasoline's engine is converted to making your car go? 5%? Any other? 15? 2%? Gosh, really? 2%? 98% wasted in a car? A modern car is higher than 15.
30.
Lower than 30.
25.
25. 25. How efficient is a well-tuned automobile when it's working at its best? 25%. 75% of the energy is lost. What would be one way of increasing the energy efficiency in machines, and a Prius does this? Reduce the number of energy conversions. Every time you have an energy conversion, you lose energy. Every time you have an energy conversion, you lose energy. So for a car, 33% is lost right off the tailpipe. 29% is heat that is not converted to mechanical. So you need a coolant system in your car, or else your car will overheat and your engine will go kaplooey. 6 is just used for pumping air into it in order for combustion to occur. 3 is lost as those pistons are firing. They rub against the walls. Some of that is just energy lost in the form of friction. Other forms of friction: 4, if you're running your air conditioner or your heating system or your radio, some of that is being lost. And finally, 25 goes into making your car go. What is the overall reaction that is involved in most examples of when we say the word burning? Hydrocarbon plus oxygen to produce carbon dioxide and water. It's what we call combustion. Wax burning is producing carbon dioxide and water and heat. In the case of a candle, we also want it to produce what? Smell. That's moving molecules. Light. All right, so here are the targets I'd like to get to today. Specific heat. Use specific heat in the Q equation and explain the heat of combustion and apply it to present energy needs. Okay, the amount of heat given off is heat of combustion. The amount of heat energy given off, or really the amount of any kind of energy given off when something is burned. What equation is used to determine the heat of combustion? The Q equation. Q is equal to M. M stands for mass. Times delta, that's the Greek symbol delta, the triangle. Delta, it's the Greek letter D. Delta T is change in temperature. That is final temperature minus initial temperature. And SH stands for specific heat. Specific heat.
Is that M times?
M times delta T times SH. All right, specific heat can sometimes be difficult to explain, so I'm going to explain it using an illustration. When I was a kid, we didn't use as many plastics as we use today. Plastics, I mean, they were there, they've been there for almost 50 years, but everything wasn't made out of plastic. So our chairs down in South Florida were metal chairs. Okay? So what did that mean? Whenever it would get frigid, in other words, when the temperatures would get down into the 50s, it would get cold. Okay, you need to understand, my elementary school had air conditioning, but it did not have heating. So I bet even you Yankees would complain if it got down into the low 50s and there was no heating. So we would get in and we would have our big heavy parkas because the temperatures were down in the 50s and 60s. And we were from South Florida, and 50s and 60s is really, really cold. And we would look at our metal chairs. Why would we look at our metal chairs apprehensively?
Because they were
Cold.
Oh my gosh. So we would, I mean, class had to begin, and we had to sit down, but it was like, oh, and we'd be screaming, we'd be rubbing the chair. What are we trying to do?
Get it warm.
We're trying to transfer our butt heat into the chair. Think about it. What is it? Where's the heat coming from? Our butt.
Your butt.
So I call it butt heat. Okay, so the heat is going into, and we're rubbing, and really, truth be told, it did not take very long to warm up that chair. And when it no longer felt cold, what does that mean to us?
The heat transfer.
The heat, enough heat transferred from our butts to the chair that what is the temperature difference between our butts and the chair? Not much. Folks, whenever you feel anything cold, what does that mean? Heat is leaving. Your body can only detect two things: heat leaving your skin or heat going in. Your body cannot detect cold. Coldness does not exist. If somebody takes their frigid hand and put it on your cheek, and you go, "Get that away from me, it's cold!" It is not cold. It just simply does not have as much heat as your cheek does. So what does your cheek have to do? Transfer heat. And what you're feeling is the heat being transferred out of your cheek and into that person's hands. So he is feeling, oh, this is nice and warm. Because where is heat going? Into his hand. And where is heat leaving?
Into
your cheek. So if you feel cold, heat is leaving you. If you feel warm, heat is coming into you. Now, a phenomenon would occur as soon you hated leaving your chair for your next class, because you would leave your chair, then you would, I warmed you. You were nice and warm. And you would go to your next class, and the next class you would look at that chair and go, and you'd be warming it up all over again. Why? Because metals have a low specific heat. That means it takes a little bit of energy and it warms up real fast. But then it'll also cool down really fast. It warms up really fast, cools down really fast. Those are metals. They have a low specific heat. Now, these are plastic chairs. And they're different. But I'm probably going to gross all of you out now, if you think about it the way I think about it. Okay? So, first period. You go in, and you sit, and it's kind of cold, but, you know. So, and it stays kind of cool for a while, and then pretty soon you don't notice it anymore. Why? Because it's plastic chair. It has a high specific heat. It takes a while for you to heat it up so that it is now the same temperature as your butt. On the other hand, you get up. It took a while for it to heat up. Guess what? It takes a while for you to cool down. So you get to your next period class and you sit down and you go, oh, this is nice and warm. That's what normal people think. People like me think, oh my gosh, somebody's butt heat is entering my butt. Oh, gross. I wonder if I can catch a disease that way. So the next time you sit on a nice warm chair, ask yourself, who was in this chair last, and do I want his or her butt heat entering my butt? Because if that chair feels warm to you, guess what? The heat is going into your butt. And where did that heat come from?
Somebody else's butt.
Somebody else's butt. So I've asked my doctor, hey, can you catch a disease by butt heat? And they've looked at me, she looks at me and goes, Vidal, just you know, what other problems do you have? All right. So, what is specific heat? The amount of energy that a 1 gram of a substance can absorb before it goes up 1 degree Celsius. Anybody new to Oak Ridge here? Nobody here is new to Oak Ridge. There's usually one person. And I love telling them, oh, so we're going to make believe that Emmy's new to Oak Ridge. Yes, Emmy. Oh, Emmy, the Oak Ridge pool. It's a heated pool. So come June 1st, it opens up and it's, the temperature's outside still kind of cool, but that water is so warm. So go up to the diving board and dive in. It'll be like diving into a sauna. It'll be so nice. I have yet to convince anyone to do that because there's always somebody who say, no, don't do it. Don't. Because even though they're in the process of filling that pool up, even though that pool will be filled up by the middle of April and will spend April and May being hit by the sun, slowly warming up, what do we know about the specific heat of water? It is really high. So it takes a lot of energy for it to warm up. So it takes a long time for it to warm up, but that also means that it takes a long time for it to cool down. The irony of it all is that those of us who are Oak Ridgers know that we go there in June and we're surprised that there's not icebergs floating on the water, right? Because that water in June is intolerable. I, for one, will not touch that pool in June. By the end of July, I start thinking, hey, let's go to the pool because it's, the temperatures are up into the 70s and it's not frigid. The irony is that it closes in the beginning of August. Guess what the temperature is finally at in August? 100. It's finally comfortable. And it's been closed down. And September, guess what? It's comfortable. And it's closed down. Okay? Why? Because it needs a lot of energy in order for it to heat up. But then, even though the temperatures outside begin to cool down, it takes a while for it to cool down as well. Do you ever wonder why the hurricane season starts in late July and ends in October? What do you need in order for you to have a hurricane? Hot water, warm water. Well, why don't you start in June when the temperatures are hot? Because yes, the air temperatures are hot, but the water temperature is still cold. So it takes a few months in the Caribbean for the water temperature to get hot enough for there to be hurricanes. So you get hurricanes in late July, August, September. And even though in September things have begun to cool, the air has begun to cool down, the water is still hot. So you can have a hurricane in September and even October because the temperature of the water is still hot because water has such a high specific heat. High specific heat. Determine whether the following materials would have high or low. In other words, ask yourself, does it take a long time for it to warm up? Or does it warm up real quick? If it warms up real quick, it has a low specific heat. If it warms up slowly, then it has a high. Let me give you one more example, and this is very important, just in case you want to bribe me with chocolate chip cookies. I love chocolate chip cookies, but I love chewy, moist chocolate chip cookies. If you have an aluminum pan at home and you intend to use an aluminum pan, don't bother bringing me chocolate chip cookies because I'm not going to like them and I won't give you extra credit. Okay, why? Because aluminum has very low specific heat. That means that aluminum gets hot very slowly or quickly? Quickly, and it also cools down. That's why, I don't know if you've ever messed around with aluminum foil straight out of the oven, almost immediately it cools down. Yeah. You can touch it. Okay, so you put the dough on an aluminum pan and you stick it in the oven. Air has a very high specific heat. So the air is warming up slowly. The aluminum pan is warming up quickly. What happens to the bottom of the cookie?
Burn.
The bottom of the cookie gets done quickly because the aluminum pan heats up quickly. So you're supposed to look at it and not take them out until the top are golden brown. By the time the air has heated fast enough or heated enough to golden brown the top of the cookies, what's happened to the bottom of the cookies?
Dark brown.
You've burnt the bottom. That's why if you want to bribe me with chocolate chip cookies, you need a baking stone. A baking stone.
What's that?
Well, it's a ceramic piece. It's a flat ceramic piece. You can put pizzas on it, or you can put biscuits, or you can put cookies. The main thing is that they have designed that piece of ceramic so that its specific heat is about the same as the specific heat of air. So it heats up at the same rate as air does. So if it's golden brown on top,
Golden brown on bottom.
it's golden brown on the bottom. And that is why baking stones are more efficient for cooking
Where do you
things.
buy them?
Pampered Chef, but by now, I mean, you can get them at, used to be only Pampered Chef, which is one of those, you know, where you have parties and they're really expensive. They're usually better quality than what you can get at Walmart, but at Walmart you can get a lower quality baking stone that works just as well. All right, oil. Does it heat up fast or slow?
Low.
Really? I think it's slow.
Well, like vegetable oil? Or
Yeah, I mean cooking oil. Cooking oil. Even motor oil heats up very. What would happen if it heat up very fast? It could possibly catch on fire. You don't want it to heat up very fast. Okay. What about water? High or low specific heat?
High.
Plastic, high or low?
High.
Plastics, most plastics are high. Here's a good example. Spatulas are metal or plastic?
Plastic. Well, both.
Okay, I'm sorry. The spatulas you would use on a grill.
Metal.
Metal. What about the handle?
Plastic. Or wood.
What does that tell you? Or wood. What does that tell you?
Yeah,
It wants to
wire.
protect your hand. So what would happen if it was all metallic?
Yeah, you burn it.
You would burn your hand. Wood. The handle on those spatulas are usually plastic or
Wood.
wood. Perfume.
Well,
Keeping in mind the whole purpose of perfume is for it to go on your body and for it to heat up fast enough so that it evaporates and goes up somebody's nose so that they notice that you smell nice. Because if it had a high specific heat, would it ever evaporate off your body?
no.
No. So if it doesn't evaporate off your body, can you smell it? Can somebody else smell it? No. It needs to be able to evaporate off your body and go up somebody's nose for them to go, oh, Gracie smells nice. Okay? Right? If it has a high specific heat, we'll never know. We won't say that Gracie smells bad, but we won't say that Gracie smells nice. What about the chemical that makes body odor, high or low?
What? Low?
I think it's high because it doesn't evaporate very quickly.
No, not sweat. Whatever chemical gives you body odor.
Oh.
Okay,
Low.
it's getting out there, isn't it? I mean, it's absorbing a lot of heat, it's evaporating, and it's going into our noses, and it's offending our noses. Alcohol, high or low?
Low.
Does alcohol evaporate quickly?
Yeah.
Low.
It can be very useful to know how much heat a chemical reaction absorbs or releases. In addition to the exothermic hand warmers that we looked at, there are also endothermic chemical ice packs for treating injuries. The ability to calculate change in enthalpy is also what tells pilots how far the fuel in an airplane's tank will allow it to fly, which I am personally very interested in making sure they get right. One of the
So, what are the heat combustions for the common fuels that we use? Methane, 55.6. Propane. Methane, of course, is heating fuel for our houses. Propane is for grilling. Hexane is gasoline. Septane or heptane is gasoline. Octane is in gasoline. So why don't we use natural gas to power our cars?
Really?
No, I mean it's not as expensive. It's just you got to store it in pressure. Under pressure, it's just more dangerous. I mean, if you get rear-ended,
Ooh.
it could potentially be a much more explosive situation. Okay, propane and methane are gases, and even though we get more energy out of them, they are a lot harder to store. What about the heat of combustion of coal? How about if we could take a chunk of coal and drop it into our tanks? That would be much better, right? Much better. Okay, so let's hold off. I think we're running out of time, right?
I have no idea.
All right, so let's try one of these questions. Yes. Remember, the equation we're going to be using is Q is equal to mass times change in temperature times specific heat, where the mass is usually in grams, change in temperature is final minus initial, and specific heat is how much energy it takes for 1 little gram of it, just 1 little gram, to go up by 1 degree Celsius. By 1 degree Celsius. All right, so here we go. Q is how much energy. Energy is Q. Mass is, well, in grams. Should we use this mass or this mass?
The first one.
I don't know. Let's put them both down, and we'll use the one that we decide is what we need. Is this right? 3 grams of wax, 50 grams of water. Okay, so the water goes from 20 to 30, so it's reversed, 30 minus 20 degrees C of water. And the specific heat is of water. Okay, does that help us decide which one we should use?
No.
Yeah.
Yeah.
Okay, if I give you the change in temperature of water, I give you the specific heat of water, then I give you the mass of water or the mass of wax, which mass should you use?
Wax. Water.
You're really
I'm
on the
just
ball
kidding.
today.
I'm just kidding.
50 times 10 times 4.18 is?
Wait, what?
50 times 10 times 4.18. The difference is 10 degrees, isn't it? Is?
I don't have it.
I lost mine. For the first
I always forget to take it to the teacher.
And
It
they're so
doesn't work.
exclusive, and I gotta find another one.
I got you. You can run it.
Let's go, folks.
50 times 10.
Bailey?
And you get it for free. 2,000.
No.
Oh, God.
Oh,
no.
okay.
I got a really big number.
Randy?
Yeah. Oh, sorry. Is that 2 billion or 2 trillion?
2090. 2090.
Oh, I did 4,018.
Thank you, Jackson. 2090. Okay, everyone, you understand how we got 2090?
Yeah, I got it.
There's another question, which is, what is the heat of combustion? Heat of combustion is measured in kilojoules per mole of that which is combusting. What is combusting? What is being turned into carbon dioxide and water? What is combusting? Read the question.
Water.
Water is being turned into carbon dioxide and water by burning. So we burn water. Water can combust.
Oxygen.
The wax.
The wax is combusting. The wax is combusting. Okay, so what we're going to have to do is find out the kilojoules per mole of the wax. So we've got 2 problems. Problem number 1, this is in joules. That's how much energy the water absorbed. Therefore, how much energy did the wax give off? Energy is not lost. We learned that from Hank Green. Energy is never lost. So if the water absorbed 2,090 joules of energy, how much energy did the wax give off? 2,090 joules. So it's okay to use, even though that's for water, it's okay to use that number because energy is never lost. So our first problem is we need to convert joules to kilojoules. How do you convert joules to kilojoules? Does anyone remember? Jeff? How many places? 2, 3. So we've got part of our answer. It is 2090 kilojoules. Kilojoules. Now we need to divide that by moles. We need to divide that by moles. Are we given moles of wax in the question? No. We're given grams of wax. Are we now capable of converting grams to moles or moles to grams? Who remembers how do you convert grams to moles? Divide by the formula mass. Okay, wax is something I need to tell you is C25H52. So that means you have 25 of carbon, which is 12, and you have 52 of hydrogen, which is 1. So it's 352 grams. So in order to find moles, we have to divide the mass of what we're trying to get, which is the wax. If you're trying to figure out what do we do with the other grams, this is what we do with the other grams. We divide it by its formula mass. And that equals 0.00. So, what do we do now? We divide these two numbers. What is it? What, Gracie?
245.8.
All right. Let's review. First thing you do is figure out who the change in temperature is for. And it should be the same person whose specific heat you are given. Then you multiply the change in temperature and the specific heat by the mass of the same thing. We could not use 3 grams because that's something different. That's candle. We needed to use the 50 grams of water. So 50 times the change in temperature, which is 30 minus 20, which is 10, times 4.18. That gave us the amount of energy that the water absorbed. The water heated up because the wax burned. Okay? That means that if the water absorbed the energy, who gave off the energy? The wax. So we are halfway there to finding the heat of combustion. Heat of combustion is measured in kilojoules per mole. So the first thing we did was move the decimal place 3 places over to get kilojoules. Then we converted to moles by taking the mass that was given to us and dividing by the formula mass, which is the sum of all the masses of each element in the formula. That gave us a mole of 0.0085. We divided these two numbers and we got its heat of combustion. Be nice if we could just stick candles in our car, but then again, same problem with coal. Candles would not burn as cleanly as gasoline does, and it would just be, well, you would first have to heat it up, turn it into a vapor. It'd be a mess. It'd be a mess. All right, let's see if you learned anything. This one is exactly the same, different questions, or I'm sorry, different numbers. I'll do it quietly on the screen. If you get stuck somewhere, look on the screen. Here is the formula for gasoline. It's C8H18. Any questions? What's the important part of this? This equation right here. Why am I making you do the rest? Because the next two labs, 2 out of the next 3 labs will be based on this problem right here. You're going to have to find the heat of combustion for wax. I think we're going to do the heat of combustion for something else. Okay? So you'll need to follow these kinds of mathematical maneuvers. Any questions? All right. So, in the play, you're going to see some lamps. They are kerosene lamps, or they're supposed to be kerosene lamps. In actuality, they're light bulbs, okay? But at one time, that's how we lit up cities. All right, you actually had an army, a small army of people who would go out every night and fill up these lamps with kerosene. They would light the lamps, and then in the morning they would come and put it out. I mean, can you imagine that? Can you imagine also being one of these people in the early 1900s? What happened to them? They started talking about the light bulb. Oh, the light bulb will never replace kerosene lamps. They did. They did, didn't they? All right, so what happened to the use of kerosene after the invention of the electric light bulb? Well, we didn't need as much kerosene. It's still used, by the way, for heating, but it's not as useful. What did chemists figure out what to do with at this time? Converting these very complex, larger molecules into smaller molecules, which would then be used in gasoline engines. Because about the same time that we got the light bulb, we got the automobile. Okay, this process is called cracking. Cracking, which I think is a cool name.
In this video, you will learn about the process of cracking, how it is carried out, and why it is done. From our video on fractional distillation, you should know that crude oil is a mixture of hydrocarbons with different carbon chain lengths. Smaller hydrocarbons have a lower boiling point and are more volatile, making them easy to ignite and more useful as fuels. Larger hydrocarbons have a higher boiling point, are harder to ignite, therefore not as useful as fuels. We use a lot of fuels in our day-to-day lives, driving cars, aeroplanes, lorries, and even heating our homes. This means there is a very high demand for small-chain hydrocarbons. However, after fractional distillation, we find that we have a large supply of long-chain molecules. The process of cracking breaks down long-chain alkanes into a smaller alkane and alkene molecule. This allows the supply of short-chain hydrocarbons to meet the demand for them, as the longer-chain alkanes are broken down into shorter alkanes and an alkene. The alkenes are also useful, as these can be used in the manufacture of plastics. Here is an equation showing that C12H26 is broken down into octane and butene. There isn't a set way that these molecules are broken down. In fact, C12H26 could also be broken down into decane and ethene, or even butene, pentane and propene, as these equations show. The large hydrocarbon is broken down in quite a random way. Just note that in each equation, of course, since we had 12 carbon atoms and 26 hydrogens going into the reaction, the same must come out. The process of cracking is carried out in one of two ways, either by thermal cracking using high temperature and pressure, or by catalytic cracking at low temperatures and pressures but using a catalyst. In thermal cracking, the large hydrocarbons are heated to temperatures up to 750 degrees C and a high pressure of 70 atmospheres. This high temperature and pressure breaks the bonds between carbon atoms to make smaller molecules. Catalytic cracking is the method used mostly in industry today. The large hydrocarbons are heated to around 500 degrees C and are passed over a zeolite catalyst. The catalysts chosen tend to break the bonds in the large hydrocarbons and make molecules of between 5 to 10 carbons in chain lengths, making them very useful in petrol. Now, at the end of this video tutorial, you should know that cracking is the process in which large alkanes are turned into smaller alkanes and an alkene molecule.
And you're probably wondering, what the heck is an alkane and an alkene? You're going to find out. We're going to learn how to draw these things, and we're going to learn how to name them. You get to learn stuff that even AP chemistry doesn't get to learn. All right? Now, you noticed that there were two ways of cracking, and cracking is very, very important in industry. There are two ways of cracking. That was by just heating it to very hot temperature, 750 degrees. What's the problem with getting things really, really hot? It takes a lot of energy. That's money. It's a whole lot easier to use a catalyst. How much of today's crude oil is cracked? About a third. That's, can you imagine how many millions of barrels of oil every year is cracked? How has the process improved? By adding a catalyst. And that's what we're going to study next.